So, good morning, everybody. I'm really happy to be with you here. And first of all, I want to thank Professor Galina for the opportunity to share a bit of the things that I work with you. I think instead of talking about myself, I think it will be more interesting to talk about my institution, the Polytechnic of Porto, the School of Engineering. So I prepared a few slides just in front of the presentation to talk about my school. So thanks, Natalia, for the opportunity to present my institution. It's called Instituto Superior de Engenharia do Porto. This is in Portuguese. If you translate to English, that will be something like the School of Engineering of the Polytechnic of Porto. It's located here, you can see in the corner. Porto is really on the west point of Europe, okay? So we are pretty far away from Ukraine. Still, we are in the same region of Europe, okay? The Polytechnic of Porto is composed by several schools, the School of Engineering being one of them. We have engineering, music and the performing arts, health, hospitality and tourism, management, technology, media arts and design, accounting and business, and education. So we are a polytechnic in that sense. We have 3 camping, roughly 20,000 students. We have research centers also. There are no institutions of higher education without research centers. And we have a pretty large number of bachelor degrees and master degrees, all according to the Bologna model. So first cycle, second cycle. Still, we don't have the third cycle, that is PhD. The Polytechnic, the School of Engineering, so ISEP, was created in 1852. So that's roughly 170 years ago. So we are already an established institution. In 1975, we jumped into the higher education system. In 1989, we integrated the Polytechnic of Porto. And more recently, we have changed the brand of our institution, which is now called Porto or Polytechnic of Porto. Some numbers about this academic year. We have 13 bachelor degrees and 15 master degrees at our school. Most of the research groups are based at the School of Engineering. A large number of projects, scientific papers, but the numbers that characterize the ISEP are most these 6,500 students, all in engineering, and roughly 400 academic staff members. All of our degrees are branded with European quality level, Euro ACE, and we have one degree, I think it's the master degree on informatics, that is accredited by ABET, which is the American Quality Accreditation Agency. So we are very committed with the quality of our degrees. And this is a picture of Porto. Porto is a very nice city located in the northern part of Portugal. This is not the best time to travel because of the coronavirus, but once we surpass this situation, I hope that everything goes back to the normal. And one of the things that I would like to do is actually visit Ukraine. So looking forward to that, okay? Now to the presentation. This is a presentation or a lecture about OpenLabs. The idea is very simple. OpenLabs are not a new solution. It's only because of this recent problem of the coronavirus that people are looking more attentively to the solution of remote and virtual labs. But the solution is on the market, has been developed more than 20 years ago. The thing is that it goes like this. Because of this situation, many classes have moved from the traditional face-to-face environment to the virtual environment. So we are now giving lectures like this one through Zoom, Cisco WebEx, Microsoft Teams, Google Meets, you name it. It's important to notice that in higher education, if you go back 20 years ago, you notice that many of the contents were transposed from the libraries to Moodle, to platforms like Moodle, Blackboard, etc. So this digitalization of the higher education space has been evolving. Okay, the last frontier. It seems like Star Trek. It's the physical labs, because people needed to go to the physical labs to test a machine, to do a circuit, to experiment something. So this is the last frontier, is the ability to run experiments on the internet. And for that, you have remote and virtual labs. So that's very simple to put it. Okay? Now, the structure of the lecture will be something like this. What are remote and virtual labs, and where do they fit in higher education? We want to see how remote and virtual labs stands as learning environments, how people can learn from virtual and remote labs. And we also want to introduce the concept of sustainability. And this has to do with the Sustainable Development Goals set up by the United Nations. So we want to show that remote labs can be sustainable learning environments. And then we conclude. So let's take two criteria. We want to look into the type of access, if it is something that is being accessed locally or remotely. So the type of access is one criteria. And then we want to look into another criteria, that is the nature of what we are accessing. If it is something that is real, nature, or something that is a computer model. Okay? If we combine these two criteria, we'll have four distant situations. So if we are talking about local access to a real thing, we are talking about the traditional lab. We have to go into the lab, use the equipment. The equipment is there, so it's a real thing. So we are talking about the traditional lab. If we have local access to something that is simulated, then we are talking about a simulation program that fits on a certain computer, that you have to go into that lab to use that particular computer because the software is only installed there. Okay? And that will be a simulation program. If you now consider that you are accessing remotely, okay, and you are accessing something that is real, then you are talking about a remote lab. You access from the internet something that is real. For instance, I could be controlling from my computer a certain equipment that is located in Ukraine or Germany. So that will be a remote access to something that is real there. If you talk about remote access to something that is simulated to a computer model, then you are talking about a virtual lab. So that gives you the four distant situations: traditional labs, remote labs, virtual labs, and access to simulation engines on a particular computer. What do we do in instructional labs? This is a question that sometimes we pose ourselves. So why do we use labs? One particular person that is depicted on that slide is Professor Alves. In 2005, listed 13 instructional goals for laboratories. For instance, one of the objectives of going into the lab is to check the validity of models. So, for instance, you have to identify the strengths and limitations of theoretical models as predictors of real-world behaviors. So when you say that the current, electrical current, is equal to the voltage divided by the resistance, this is a formula. This is a mathematical modeling or a certain phenomenon. If you go to the lab and you take a battery and you take a resistor and you connect the two and you measure the voltage and you know the resistance and you measure the current, you will see that these measurements will be the same or similar to the ones that you have been able to calculate from the formula of current equal to voltage divided by the resistance. So this will be the formula, and this is the real thing where you measure the voltage and the current. So one of the things that you actually go and do in the labs is to verify that these models, these mathematical formulas, are correct, okay? And all students go through this, okay? It's important, it's interesting to mention Max Planck here. Max Planck was a researcher, I think from Germany, if I'm not wrong. If I'm wrong, I'm sorry. An experiment is a question which science posed to nature, and the measurement is a recording of the nature's answer. So whenever you make a measurement, you are seeing what is the response of nature, okay? So it's very important for all scientists and all engineers to have skills, to have competence in terms of labs and experiments, okay? So if we go back 200 years ago, roughly, or more than that, we could say that the first engineering schools, basically you had two environments. You had to be fluent in doing calculus, and you had to be fluent in hands-on. These were the two scenarios that all engineering schools, or the first engineering schools had, hands-on and calculus. And this goes back to the 17th century, to the Royal Society. For instance, Newton was a member of the Royal Society. That they had this motto saying, it's not enough for you to say that something is true. Other people need to verify that through an experiment. So it's not just about your word. It's about going into the lab and repeating an experiment and having the same results. Then I can for sure know that you are doing the right thing, or this is correct. And this is their motto, nullius in verba. Don't believe just in the words. Do it. Experiment. Get results. Okay? Again, Max Planck goes into this idea, the measurement. And Lyle Feisal also in his paper, he says that there is a value in combining theory with practice. Okay? So this was real simple, and even for lectures in higher education, this was quite simple. But life is not always simple. So in the 20th century, you had a new companion, the personal computer. And the personal computer is like a slave. It does calculations very, very fast. Okay? So you had the possibility to, instead of doing your calculation by hand, put a code in a program in the computer and having the computer running that program. So the first simulations appeared on this. So you have a new environment. You have the capability or the ability to do calculus by hand. You need to go into the lab and do experiments. And you can go into the computer and have a kind of virtual lab. So you see that this scenario, very simple, of hands-on calculus, now began to get more complicated or richer in that sense. Students needed to be fluent not only on two environments, but also on another third environment. And at the same time, teachers needed also to master this new scenario. PCs were early quite expensive, but they began to get more cheaper and cheaper. So eventually, every university, every lab, every workbench now has a computer. Okay, everybody has a computer, has a smartphone. So computers are everywhere. So back into this. So the whole idea was that you had one computer in every workbench, and this computer was connected to instrumentation, and this computer was connected to the net, so you could access the computer from anywhere, so you could connect to the instrumentation that was on a workbench, so you could actually access the lab through the computer that was there. So this gives an idea of a remote lab. Again, this is another landscape, another scenario. So if you combine all of this, look, from the simple situation where you had just the hands-on and the calculus, now you have hands-on, calculus, virtual lab, and remote lab. So this means that the educational scenario, it's richer. Teachers can ask students to go into the lab and do something, or teachers can ask the students to run simulation and compare against the experiments they have made in the lab. Or teachers can ask the students to go home, access the remote lab, get real measurements, compare with simulations, and then check everything with calculus. So this is a richer environment. And at the same time, it's a more difficult environment for both students and teachers, because you have to be fluent, not only just in the lab, not only when you are doing exercise and exercise during the exams, but you have many different opportunities to learn. And so that's the whole idea, okay, is to use these different resources to have students learning more and better, okay? So this is, okay, it seems to be quite natural. Okay, why didn't everybody think of this? So about 8 years ago, three researchers, they looked into 100 years of engineering education. They took proceedings, books, transactions, and they put up this idea. What were the major transformations in engineering education? And they came up with five major shifts or major transformations in engineering education. They said, first, there was a shift from hands-on and practical emphasis to engineering science and analytical emphasis. That's why in engineering we have so much maths and physics on the early years, okay? The second shift was everybody started talking about outcomes-based education, the learning results, accreditation, quality, etc., etc. The third shift was engineering design project. We had a project in the first year, integrating courses, where you have to combine the knowledge from different courses, up to the end where you have a final engineering design or project at the end of your degree. So there was an emphasis on this, on design. The other thing which we noticed also in engineering education was that people started talking about psychology, learning, education, social behavioral science. So there was a concern about, okay, how do students learn? How do we have to teach? What is active learning, active teaching, project-based learning, problem-based learning, And the other one, which you all know, is we started to see more information and communication technologies into the learning process, into education. Things like Moodle, applications, simulations, etc., etc. So if we look into this last one, we can see a number of things. Content delivery through television, the internet. We are seeing this class right now through Facebook or YouTube or whatever. program instruction, personal response systems like clickers, intelligent tutors, simulations, game-based learning, remote labs, grading, you name it. Okay, so we are witnesses of this transformation. Okay, so we are now seeing the big picture, okay, what happened in engineering education. So let's now look into the more particular case where you are preparing a certain course and you want to use remote and virtual labs in your course. And this is from the teacher's point of view and the student's point of view. Well, aspects that teachers need to have in mind. First of all, the course syllabus. What are you teaching? What are you talking about? Is it thermodynamics? Is it electrical circuits? Is it, chemical reactions? Whatever. So you need to look into this. What are we teaching or learning? Then you need to plan. You need to do, okay, I have a certain number of theoretical classes. I have a certain number of practical classes. I have these labs. These are the learning goals for my course, etc., etc. So the important thing here is to plan ahead. And a part of that plan is the existence of remote and virtual labs. So for instance, if you go into this video, you'll go to the testimonial of a lecture at the Purdue University in the United States. Purdue University is one of the first universities that have a faculty entirely dedicated to engineering education. And she talks about how do you use remote and virtual labs, okay? I don't know if I click on this, if you will be able to actually see the video. And
we've had a number of questions related to how are the engineering labs going to be getting moved to the virtual space. And the quickest answer for that is it depends. And so there isn't one solution that's going to work for every instructor and every course. So my recommendation is the very first thing to think about is what were the learning objectives associated with that lab? What were the learning goals? What were students supposed to be able to do and know at the end of the semester?
Okay. Natalia, could you please tell me if you have listened to if there was sound?
Yes, I listen.
Okay. So you see that this lady, this researcher tells it all has to do with the learning goals. Okay. Whatever remote lab or virtual lab you are going to use, it has to contribute to what students need to learn. So the important things are the learning goals. It's not about the technology that you are going to use. It's about what you are going to learn at the end of the course. Okay? So going back to the presentation, it's important for the lecturer to understand what are the available resources, materials, infrastructures, tools, environments, etc. And you also need to consider that you don't know everything immediately. So you need to consider that students need time to understand how to use the remote lab or how to use a certain simulation or how to use a certain virtual lab. So it's important to consider that there is also a learning curve attached to any new technology that you are going to use in your lectures. Okay? People need time to learn, simply put. Okay? And then you have to see that we are not all the same. Boys learn differently from girls. There are different learning styles. Even the teachers are different. So there are different teaching methodologies, diversity, etc., etc. All of this goes into how do you plan your course. One of the things that is pretty much consensual is that if you plan for a regular and quick feedback, that will be helpful for everybody. Students like to have an immediate answer to their questions. So if you take 1 week to respond to a message from your student, forget it. You need to be quick on the feedback that you give to your students, because they have the problem in their mind. If they do an experiment and they get some result that is not the same, they want to spot the problem there. They want some instant feedback. Hey, teacher, I'm not being able to do this. What is happening? I'm trying to do the right thing, but I get this strange result. And if you don't answer in a reasonable time, he will forget that. Okay? So whenever there is a doubt, that is the best moment to help a student, because the mind of the student is on that problem. Okay? So regular and quick feedback. And then you need to consider assessment, because at the end of the day, at the end of the course, you need to give a mark, a grade to your students. So feedback so assessment is a part of this game. Okay? So you want to combine individual, group assessment. You want to give equal opportunities to everybody, the same difficult level, because you can consider different types of assessment. But when you consider different types of assessment and even individual assessment, you need to be very careful. You don't want one student to come to you and say, hey, professor, his exam is much simpler than my exam. You don't want these kind of things, okay? So you want to promote collaborative work during training, independence of results during individual assessment, etc., etc. All of this is part of what a teacher needs to do and what students need to do during a course. And now, let's see how a remote lab works. So, I have two examples here, one remote lab and one virtual lab, okay? I am going to access the remote lab and show you how this works. So we are now trying to access a remote lab. I'm going to change into English in Brazil. So we are crossing the Atlantic and going to control things in Brazil. We are going to control light bulbs. So it's still night over there, I think. So we want to access this remote lab. You have a very simple circuit with light bulbs. And light bulbs are interesting because their resistance depends on the heat. So the hotter the light bulb is, the more bright it will be. So if I connect this circuit, so S2 here on the bottom, I don't know if I can make it, it's larger now. And if I control S1 now, and now I can make questions to the students like, if I connect S3, and when I connect S3, the three light bulbs that are on your left side, they are in parallel. They will be connected in series with the light bulb that is there on the top right corner. So the question will be, what lamps will be brighter? The three lamps in parallel or the lamp that is alone? I explained the theory, and now I'm making a real question to you. And so students will say, it will happen this or that. And then we can check what is the reality, because this is no simulation. This is a real thing. We are controlling real light bulbs. So when I connect S3, you will see that the lamp that brights more, it's the one on the right top. Okay? Now we are seeing this. Oh, this is what is happening. But we cannot do measurements here. I cannot see what is the temperature, what is the voltage, what is the current. So one good thing is actually to combine these kind of experiments with simulations, because in simulations, we can actually go and pick and see what happens. So we'll go back into here. And if we click here, this is a link, a direct link to a simulation of the same circuit. I will put it there, okay? I will put it here, let me go back here, Control C, go to the chat window, Control V, and if you click on the link that is on the chat window now, you can open the same simulation. There is no problem here because we are running a simulation, so everybody can click on the simulation that we all see what is presented to me. We cannot do this on the remote lab because we cannot control the light bulbs at the same time, everybody, because that will be impossible. You can, oh, I want to close this one. No, I want to open this one. Who is in charge here? Who is actually controlling the experiment? So a remote lab is the real thing. Simulations, hey, they are code. So we can use everybody at the same time, the same code. There's no problem on that. So look, if we close here, and you can experiment on yourself, you can do whatever you want on the simulation, okay? You can try different combinations. So that's important because when you are teaching, you also need to give time for the students to learn, to understand what is going on. And sometimes they need time on their own, or they need reflection. So they need to control their own circuits. They make their own questions. And this is possible in a virtual lab. It's not so possible in the remote lab at the same time. But the good thing of the remote lab is that you can go home. Oh, nobody's using the remote lab now. Let me use it now. Click. And if you have some kind of booking system, you can book the remote lab. You can say, oh, from 2 to 2:30, the remote lab will be mine. And you book that. It's possible to do that with a remote lab. Okay? So you see here that the light bulb that is more bright is the one on the top. And if you stop this, or you just put the mouse on top of the light bulb, you can see below the temperature. It's around 1,900 Kelvin degrees. You can see the resistance is about 713 ohms. So you can take values from the simulation. So it's important to see that remote labs are good for certain learning goals. Virtual labs are better for other learning goals. In a simulation, you can stop the simulation. You can make it faster. You can make it slower. This is not possible in a remote lab or in a traditional line. You cannot play with time, with nature. The time is what it is. But in a computer model, in a simulation, you can do whatever you want. You can reverse even the phenomenon. So these are different scenarios for people to understand a certain phenomena. Okay? So I hope you are enjoying the virtual lab. I'm also going into the remote lab, and I will leave the remote lab now, and I will copy into the chat window the address to the remote lab. So if you want to go there and try of your own. There are more remote experiments there. There are experiments with Arduino, robots, whatever, okay? So you have here some kind of resources that you can use on your lectures or your learning process. So the thing is that when we are taking a degree at university, we do a lot of experiments. For instance, in electrical engineering, you understand light bulbs, robots, machines, etc., transistors, So there are many labs in a real university. So let's try another one. Let's try one for electronic circuits. Many students, when they are taking a degree in electrical and electronics, they use this kind of material, a breadboard for connecting circuits. This is used all over the world. You go to Argentina, to China, to Japan, to Ukraine, to Portugal, to Africa, to South Africa. And if you go into a lab of electrical engineering, you see this. You see a breadboard, and you will see a DC power supply, an oscilloscope, a multimeter, and a signal generator. This is pretty much universal. So if you go into this lab, okay, let me put it larger. Oh, welcome to OpenLabs. Let's try signal processing security electronics. Go to the electronics laboratory webpage. Okay, and it says interested, go to our demo page. So we go to the demo page and we do log in as a guest. This is good because we can actually run experiments as a guest. Okay, show details, visit this website, no problem. Let me put my email. So you should put your email here just to say who you are, and you enter. So they know who you are. And you see on the left side now that you have access to a guest course. It's here, student guest course. So I'll click here on guest course and start experimenting. And here you have. You have access to a breadboard, a multimeter, a function generator, an oscilloscope, and a DC power supply. So let me do a very simple experiment. I'm going into the breadboard, and I'm going to connect. I choose a color for the wire, for instance, red, and I connect the function generator to the oscilloscope, channel 1. And then with a black wire, the ground to the ground. And then I go to the oscilloscope. Both channels are on, so you see, you can switch on and switch off the channels, the oscilloscope channels. And I go into the oscilloscope and let me put, I don't know, a 2 kilohertz square waveform, amplitude 1 volt peak to peak with no offset. And then we go to the oscilloscope, we click on oscilloscope, and when we do perform a measurement, what will happen is that the signal generator will be connected to the oscilloscope. The oscilloscope will measure a number of for a number of time during a period of time, and then you get the results. So this is a real experiment done, in this case, in Sweden. There is a signal generator there, there is an oscilloscope there, there is a matrix board, the two will be connected, and you will get real measurements done here at this time in Sweden. So we do perform measurement, and here you have the real signal. Now we can put it here, change a little bit the time, and we should do perform measurement again. Now we can see here the signal with the noise, etc. Because we are measuring a real signal, okay? Let me put some more detail here. Perform measurement. And you see this lovely noise here on your measurement, okay? The good thing about this particular lab that I will talk a bit more is that all experiments are done in 1 second because they are electrical signals. That means that many students can be using the remote lab at the same time because not everybody will click on perform measurement on the very exact time. And even if 2 or 3 students click at the same time, 1 second to serve the first student, another second to serve the second student. So that means that the third student will have to wait for 2 seconds to get his results. And 2 seconds is acceptable. So there are remote labs which you need to book. Say, hey, only me can be controlling the remote lab. Sorry, folks, but for 15 minutes, the lab is mine. For instance, when you are controlling a robot, you cannot take everybody controlling the robot at the same time. In this kind of remote lab, we call it a batch mode remote lab, because experiments take only 1 second. It's possible to serve many students at the same time. Okay, so what you could be doing, everybody here, will be using this particular remote lab, and I could be teaching something, and another student can be trying another circuit. So back to the presentation, and let me talk a bit more about this particular remote lab that is called VISIR, or Virtual Instrument Systems in Reality. This particular remote lab was developed by Professor Ingvar Gustafsson in Sweden. And he had a vision, saying, okay, he read about Max Planck, and he said, oh, a measurement is an answer for nature. But this answer can be taken in a local lab, or it can be taken remotely. So that was the idea. Experimenting could be compared to conversation with nature. The experiment asks and nature answers. The tricky thing is formulating a useful question and, above all, interpreting the answer. The only way to learn the language of nature is performing many experiments in laboratories that can be hands-on, traditional, or remote. And this was his motivation for creating VISIR, allowing students to do more experiments with electrical and electronic circuits. So basically, what we have with VISIR is we have a server, a computer, and we have an instrumentation system based on PXI from National Instruments. So you have on this particular PXI an oscilloscope, a signal generator, a DC power supply, a multimeter, and you can see here on top of the PXI system what is a matrix, because when you connect different components in a breadboard, you do different wiring. So you need some kind of programmable matrix. And you can see here on this particular slide that when you wire these two components, a capacitor and a resistor, and you connect them to the signal generator and to oscilloscope, in reality, this same resistor is there on the board. So when you are doing an experiment, you are doing an experiment with that resistor. There is a real resistor there. So this is no computer, no simulation. There is no better model than the real thing, okay? So if it is 20 degrees in Sweden, you get a certain value. If you have this same remote lab in Ukraine and it's 15 degrees there, you get a different result because the resistance will depend upon the temperature, okay? It's true that you can do this in simulation too, but it's more complex, okay? This particular remote lab called VISIR was distinguished as the best remote lab in the world in 2015 by the Global Online Laboratory Consortium, okay? And in 2018, the Professor Ingvar Gustafsson died in September 2017. And the number of persons that worked with him, we proposed that he will be a recipient of this Francesco Maffioli Award that is given by the European Society for Engineering Education. And he won the first prize. And this is we are very, very happy because this happened, because we believe that Professor Ingvar Gustafsson made a real important contribution to engineering education. Now, there's a legacy. Professor Ingvar Gustafsson, at a certain time, he decided to open all the code for VISIR. So that's why the name of this presentation is OpenLabs. And so there are VISIR laboratories at Sweden, Spain, Austria, Portugal, India, Georgia, Brazil, Argentina, Morocco, Costa Rica, Germany, next to Natalia in Dortmund, there's a VISIR lab, okay? And most recently in the United States, okay? So there are VISIR labs now all over the world. Let me now give you a different picture for remote labs. Let's see how remote labs can be sustainable. We'll see this. You can see in this picture, in this slide, a very typical scenario. Equipment, DC power supply, signal generator, the oscilloscope. I'm talking about the picture on the left side, bottom side, okay? Top, bottom, left corner. And there is a lab script, so student is supposed to do a certain kind of actions, a procedure, connect this, measure this, etc., etc. You can see the breadboard there, and you can see that we are using real components. So it's important that students also use real components, use the real lab to have their capacities in terms of controlling instrumentation. But what happens is that because imagine a course or a degree with 200 students, we need to provide components, labs, equipment for all of them. And if you look into the lab, there will be one class going in, another class going out. So there is no time. So students need to take the components. Other students come in, they put components. And at the end of the semester, look at this on the top right corner. It's garbage. It's impossible to, okay, let's put this again into the shelves. No, this is going into the garbage. And if you look into the components there, they also get damaged because you bend the wires. And after you use this transistor for 100 times, 200 times, it will break. So, garbage. Okay, this is a real scenario. And the same for integrated circuits there. So, you see that students go into the lab, they take a breadboard, they take components, they do the wirings, okay? At some part, this is not the important thing. The important things are the measurements. Okay, once you master these, the connections, hey, mounting the circuit, demounting the circuit, mounting the circuit, demounting the circuit, it's a waste of time. Because I'm interested in tuning the circuit, understanding, what if I change this resistor and I increase the voltage, what happened here? So at sometimes the learning goal is not mounting and demounting circuits, it's understanding the circuit. And this can be done with a remote lab. So you see here, the matrix, the components are there. You see the resistors, etc., the operational amplifier, etc., etc. So let's look into this. How much does one resistor cost? One resistor. If you go into the bottom, it says here that if you order more than 250 resistor, they will cost something like 3 cents. So one resistor costs 3 cents. 3 cents is nothing. For a university, hey, how many resistors you want? Let's buy 1,000 of them because you need them for all students. But now let's look into the problem. One resistor is typically used 100, 500 times because you have to put it, bend, take it out, bend again, put it, etc. So let's say, okay, one resistor used 100 and 500 times. And then it gets damaged or mixed with other components and goes into the garbage. If you go into VISIR, and because VISIR is a remote lab, it's accessed through computers. Computers are good in counting the number of times a certain experiment has been done. So there is one particular resistor at UNED that has been used more than 1 million times. So students have done experiments with this particular resistor more than 1 million times. The same resistor is there because it's there, it's used, another student comes, another experiment, 1 million times. So if we divide 1 million times by, let's take the higher number, 500. We have 1 million divided by 500, 2,000. 2,000 multiplied by 2.86 cents. We save, with only one resistor, 65 euros. With only one, we save 65. So if we use 100 different resistors, we save almost 6,000 euros in doing experiments. So a remote lab is also a sustainable way to allow students to do more experiments. And this is important because we want the students to do more experiments. And at the same time, we want to cut costs for the university. So it's combining the best of the two worlds. Don't use too much money, allow students doing more experiments. Perfect. Everybody goes happy. But the situation is like this. If you go into a lab for electronics, look at the number of components you need. You can see on this particular slide, look at this, the number of resistor capacities you need for supplying just one lab. Now, this is the side of the matrix board. You cannot place here all the components that you have here. It's impossible. So that's why you need so many VISIR labs around the world. Because in one lab, you can run these experiments with these components. For instance, in Brazil, we can run these experiments. In Sweden, we can run another experiments. In Germany, we can run another experiments. So the whole idea is that having a federation of remote labs allows to serve many different institutions. So the word here is cooperation. Cooperation among universities. Conclusion, okay? And we'll leave 10 minutes for questions and answers. Only by opening instructional labs to both teachers and students, by virtualizing them or making them remote accessible, will it be possible to guarantee practical classes in situations like the present one, okay? So students are at home, they can do experiments either in a virtual lab or in a remote lab. At the same time, we want students to do more experiments, to be more fluent on the language of nature, okay? And we don't want to have universities having an higher cost with this. So we want to combine the best of the two worlds, more experiments, but at the same time, save money. And finally, because we want to have a better education, or a quality education. It's only when we offer hands-on simulations, remote experiments, and we combine all of them that we can offer a sustainable scenario where students acquire more and better experimental skills. And that's the ultimate goal. It's to train better engineers. Thanks.